Now we're about to work our way toward our last theorem, which is the complex conjugate theorem. And let's start with something called the fundamental theorem of algebra. So as you might imagine, it's a pretty important idea because it is the fundamental theorem of algebra. And it just says something very simple. It says that every function defined by a polynomial of degree 1 or more has at least one complex zero. Now, what do we mean by complex? Remember back in chapter 1, we talked about complex numbers, and we said that all numbers are considered complex. A complex number is just a number that has both a real and imaginary part. A number that's fully real has an imaginary part that's zero, and a number that's fully imaginary has a real part that's zero. But every number can be thought of as a combination of both a real part and an imaginary part. So all the fundamental theorem of algebra is saying is that every function defined by a polynomial of degree 1 or more is going to have at least one complex zero. So it will have a zero, but it might not be fully real. And then we also have the number of zeros theorem. So this says a function that is defined by a polynomial of degree n has at most n distinct zeros. Now, by distinct, we mean different. So a polynomial of degree 3, for example, could have up to 3 different zeros, but it can't have more than that. So just to sum up, a polynomial of degree n can have n distinct or different zeros, and therefore it's possible for a zero to occur more than once. The number of times a zero occurs is referred to as the multiplicity of the zero. So here I have a function that's already been factored, and it's been factored into x minus 3 squared times x plus 1 to the 5th times x minus 7. So you can tell that the zeros are 3, -1, and 7. But because this x minus 3 factor is squared, the 3 is actually a zero for two separate factors. So we would say that the zeros are 3 with a multiplicity of 2, -1 with a multiplicity of 5, and +7 with a multiplicity of 1. In other words, 3 is a zero for two of the factors, -1 is a zero for 5 of the factors, and 7 is a zero for one of the factors. And so here finally is the conjugate zeros theorem. So this says that if f of x defines a polynomial function and all the coefficients are real, then if a plus bi is a zero of your function, then a minus bi will also be a zero of the function. You might remember back in chapter 1 we talked about complex conjugates. We talked about how if you multiply a complex number times its conjugate, you get a real answer. So here again is that conjugate idea. So one more time, if a plus bi is a zero of our function, then a minus bi will also be a zero of the function. So now here is example 6, and this says find all the zeros of f of x equals x to the 4th minus 7x to the 3rd plus 18x squared minus 22x plus 12, given that 1 minus I is a zero. Now if we think about the complex conjugate theorem that we just saw, if we know that 1 minus I is a zero, then we automatically know that 1 plus I is also a zero. Now according to the number of zeros theorem, we know that this polynomial can have up to 4 distinct zeros, and we already know 2 of them, so how will we find the last 2? Well, if we do the synthetic division with 1 minus I in the box, and then we take that quotient and do another synthetic division with 1 plus I in the box, then the quotient we get from that second synthetic division will contain the 2 zeros that we don't yet have. So let's go ahead and do that. So I'm going to go ahead and copy down the coefficients from our polynomial, and I'm going to put 1 minus I in the box. Now, Is it a little more complicated to do synthetic division with a non-real number? Yes, it is. But it's okay. You'll just have to remember that when we multiply complex numbers together, we use the FOIL method. And remember that I squared is equal to -1. So follow along with me and work it out on paper yourself, as we go. Make sure that you're doing it too, so it's all sticking with you. And I think you'll remember how we were multiplying complex numbers back in chapter 1. Okay, first we pull down, and then we multiply 1 minus I times 1. Of course, that's 1 minus I, so that goes here. And then we add. Remember, when you add complex numbers, you do real plus real and imaginary plus imaginary. So -7 plus 1 is -6. And then there's no imaginary part here, so 0 minus I is minus I. So that's going to give us -6 minus I. Now we multiply 1 minus I times this number. And that's not something you can do in your head. That's definitely something I would have to jot down. So I'm going to come over here and do that. And so using the FOIL method, first times first is going to be -6. Outer times outer is going to be minus 1I. Inner times inner is going to be plus 6I. And then last times last is going to be plus I squared. But remember, I told you I squared is equal to -1. So plus I squared becomes -1. And now we combine like terms. -6 minus 1 is -7. And -I plus 6I is positive 5I, and that needs to go here. Okay, now we add. 18 minus 7 is 11. And 0 plus 5I is plus 5I. And now we'll need to multiply this number times this one. So I'm going to erase this scratch work, and I'm going to do 1 minus I times 11 plus 5I. So again, FOIL method. First times first is going to be 11. Outer times outer is going to be plus 5I. Inner times inner is going to be minus 11I. And last times last is going to be -5I squared. Now remember, I squared is equal to -1. So -5 times -1 is positive 5. Now let's combine like terms. 11 plus 5 is 16, and 5I minus 11I is -6I. That goes here. Now add. -22 plus 16 is -6, and 0 minus 6I is just minus 6I. And now we multiply again. So 1 minus I times this number is going to give us -6 minus 6I plus 6I plus 6I squared, which simplifies to -6. Then when you combine like terms, you'll notice that the outer plus inner terms add up to 0. So we end up with a real number here as our final answer. We're going to have -12 here, and that's going to give us 0 for a remainder. Now that should not be a surprise, because they told us in the problem that 1 minus I is a 0, so we should fully expect a 0 here. Now if there are 4 zeros and we've used up one of them, there are 3 zeros left in here. We know that 1 plus I is one of those zeros. So now I'm going to do synthetic division using these coefficients, but I'm going to do it with the 1 plus I. So now pull down the 1. 1 plus I times 1 is 1 plus I. That goes here. Now combine like terms. You'll notice this time as we go through that on the bottom row we're going to get all real numbers. So that's going to make it easy to find the last 2 zeros. So now -6 plus 1 is -5. The i's add up to 0. We just have -5 here. Now to multiply -5 times 1 plus I, really all we're doing is distributing a -5 in here. So 1 times -5 is -5, and I times -5 is -5I. That goes here. Now add 11 minus 5, that's 6, and the i's add up to 0. Now multiply 1 plus I times 6, that goes here, 6 plus 6I. Now we add here and we get -6 plus 6, and that's 0. -6I plus 6I, also 0. So we get 0 for that last remainder, and that's what we expected because we knew that 1 plus I was a 0, so we knew that the remainder would have to be 0. Now let's see where we are. we're supposed to be finding all the zeros of this fourth degree function, and so far we have divided by the binomial that has 1 minus I as its zero, and this is what was left. So since this was a coefficient of x to the fourth, this would now be the coefficient of x to the third. Then we divided by the binomial that has 1 plus I as its zero, and since this was the coefficient of x to the third, this would be the coefficient of x to the second. So all we have to do now is find the two x values that would cause this remaining expression to equal 0. So what is this expression? This is going to be x squared minus 5x plus 6. And if we can find out what causes this to equal 0, then we will have found our last two zeros for this big function. So we'll need to factor this and find out what x values make these two factors equal 0. So x squared is going to break down into x times x. Then the last times last made a positive number, so the signs need to be the same. They both need to be negative. And then last times last is 6, so of course we need 3 times 2 to get the outer plus inner to add up to negative 5x. So of course if x minus 3 equals 0, that would mean that x has to equal 3. And if x minus 2 equals 0, that would mean that x has to equal 2. So just to collect all of our zeros in one place, they told us in the problem that 1 minus I was a 0, and then we used the conjugate zero theorem to figure out that 1 plus I was also a 0. And then after we did the synthetic division, we were able to find that 3 is a 0 and 2 is also a 0. So here is our final answer. And we know that this is all the zeros that this function can have because it was a fourth degree function. So the largest number of distinct zeros it can have is 4, and that's what we found. Now let's try this one. This is a very similar one. So again, I would recommend that you pause the video and try this one on your own. And keep in mind the conjugate zero theorem and the number of zeros theorem. Try this by yourself. And now I'll go through it with you. So this says find all the zeros of x to the third minus 7x squared plus 17x minus 15, given that 2 minus I is a 0. Okay, well first off, if we know that 2 minus I is a 0, then we also know that 2 plus I is a 0. And from the number of zeros theorem, we know that there can only be up to 3 distinct zeros for this polynomial. We already have 2 of them, so we'll just be finding 1 at the end to make the total of 3. So let's go ahead and set down our coefficients, and we'll put 2 minus I in the box. And now I'll go through the multiplication a little faster this time, and you can pause the video as needed. And here we go. So pull down the 1, then 2 minus I times 1 is 2 minus I. Now add, and we'll get negative 5 minus I. Now multiply 2 minus I times negative 5 minus I, and I'll do that over here, but I won't walk through it all the way. There's what you get from the FOIL method. That adds up to negative 11 plus 3i, and that goes here. Now add, and you're going to get 6 plus 3i. Now we need to multiply 2 minus I times 6 plus 3i, and using the FOIL method, we're going to get 12 plus 6i minus 6i plus 3, and that's going to add up to 15. So 15 goes here, and of course, then when we add, we get 0, which we knew we had to get because 2 minus I is a 0. Okay, now we'll need to do another round of synthetic division using 2 plus I in the box. So pull down, 2 plus I times 1 is 2 plus I, that goes here. Then add, and we'll get negative 3. Then 2 plus I times negative 3 is going to make negative 6 minus 3i. And then when we add, we get 0. So now remember, we can only have 3 zeros total, and 2 of the zeros are here and here. And so what's left here just contains 1 0. So if we started with x to the third and we did 2 rounds of synthetic division, this has to be the coefficient of x to the first. So what we have here is just x minus 3, and we need to know what value of x makes that equal 0. So of course the 0 we get from here is x equals 3. And now finally our 3 zeros are 2 minus I, 2 plus I, and 3. And now we're going to talk a little bit about Descartes' rule of signs, and this will be our last topic for this section. René Descartes was a French philosopher and mathematician who lived back in the 1600s. He touched a lot of different areas of mathematics, and one of the things that he did was develop the XY coordinate system that we still use today. And another thing he did was he was instrumental in getting the quadratic formula into the form that we know it as today. But here is an important discovery that he made regarding polynomials. And this would have been probably most useful back in the days before computers, when mathematicians had to find zeros of polynomials without any help from a computer. If you had a big P over Q list to dig through, Descartes' rule of signs could help you eliminate some potential choices. So let's take a look at it. It just says, let f of x define a polynomial function with real coefficients and a non-zero constant term. So we have to have a constant term in order to use Descartes' rule of signs. And assume that it's written in descending powers of x. Then we can know two things for sure. The number of positive real zeros of our function either equals the number of variations in sign, or it's less than that by some positive even integer. And then the number of negative real zeros equals the number of variations in sign for f of negative x, or it's less than that by a positive even integer. Now I know right now this just sounds like a whole lot of words and it sounds really complicated, but I think when we get an example it's not as complicated as it sounds here. So let's go ahead and look. Here's example 7, and this says determine the different possibilities for the number of positive, negative, and non-real complex zeros of this function. So we have here x to the 4th minus 6x to the 3rd plus 8x squared plus 2x minus 1. And I'll just copy that here. Now remember, Descartes' rule of signs said that the number of positive real zeros is either equal to the number of sign changes in our function, or it's less than that by an even number. So let's count sign changes here. It starts off positive, then the next term is negative, so that's one sign change. Then the next term is positive, so that's another sign change. This next term is also positive, so that's not a sign change, but then this last term goes back to negative, so that is a third sign change. So now remember, Descartes' rule tells us that the number of positive real zeros is either equal to the number of sign changes, or it's less than that by an even number. Now the smallest even number, of course, is 2. So the number of positive real zeros that we have here is either 3, or it's less than that by 2. So 3 minus 2 is 1. The number of positive real zeros here is either 3 or it's 1. You can't go smaller than that by an even number again, because if you take away 2 again, you go into the negative numbers, and that doesn't make sense. Okay, now let's determine the number of possible negative real roots. So remember, for that we have to look at f of negative x, and in order to determine f of negative x, we'll have to plug negative x into each of these terms. Now I know that sounds like a lot of work, but it really turns out to not be any work at all, because you know that a negative raised to an even power comes out positive, and you know that a negative raised to an odd power comes out negative. So what's going to happen here when you plug in negative x? Well, negative to the 4th power is positive, and x to the 4th power, of course, is still x to the 4th. See, it's not going to change the term if the power is even, but if the power is odd, it is going to change it. So let's go here and plug in negative x. Negative x raised to the 3rd power would be negative x to the 3rd. So negative 6 times negative x to the 3rd would be positive 6x to the 3rd. See how the only effect that had was to change the sign of that term? Okay, so what's going to happen here where we have an even exponent? Well, we know that raising a negative to an even power gives us a positive result. So this is just going to be positive 8x squared. And now plugging negative x in here, that's going to make negative 2x. And then, of course, this stays the same. So again, I just want to make sure you understand the bottom line here for finding f of negative x is that all of your terms in your polynomial are going to stay the same if the powers are even, but they're going to change sign if the powers are odd, and that's how you'll determine f of negative x. Now let's count sign changes here. This starts off positive. Here it's still positive, then it turns negative. So there's one sign change, and then in the next term we don't get a sign change. So the number of negative real zeros for this function is exactly 1, and you can't go less than that by an even number because less than that by 2 would go into the negative numbers. Now let's kind of sum up the different possibilities that we have here. We know from the fundamental theorem of algebra that the number of zeros this polynomial should have is 4. Some of them are going to be real and some of them might be non-real, or what we sometimes call complex. So let's see what the different possibilities are. If the number of positive real zeros is 3, and we know the number of negative real zeros is 1, well, that's a total of 4 zeros. 3 positive real zeros plus 1 negative real zero makes 4 zeros. That's all there can be. So that's one way things can happen. Or if the number of positive real zeros is only 1, and the number of negative real zeros has to be 1, well, 1 plus 1 is only 2. And there have to be a total of 4 zeros. So the other 2 are going to be non-real. So 1 positive real plus 1 negative real plus 2 non-real makes a total of 4. And that's the other way this can happen. Now just to give you a visual idea of what is actually happening here, here is the graph represented by this polynomial. Notice that it crosses the x-axis 4 times, so it has 4 real zeros. 3 of them are positive, and 1 of them is negative. You're not responsible for drawing this graph by any means, but I just wanted to show it to you as a reminder that when we're talking about real zeros, those are actually on a graph represented by x-intercepts. So you can easily see here the 3 positive zeros and the 1 negative zero. Now here is a function for you to practice on just to make sure that you have a good handle on Descartes' rule of signs. And so I would encourage you to pause the video and try this one by yourself, and then I'll go through it with you. Okay, so here we go. We have f of x equals 5x to the 4th plus 3x squared plus 2x minus 9. Now to find the number of positive real zeros, we count the sign changes in f of x. So this starts positive, stays positive, then it turns negative. So there's only one sign change, so we know now that there's one positive real zero. And now let's look at f of negative x. So remember, to do this, we plug negative x into our function, but all that does is it leaves the terms with even exponents unchanged, and it changes the sign of terms that have odd exponents. So this 5x to the 4th stays the same, 3x squared stays the same, 2x will change to negative 2x, and then the constant stays the same. And let's count sign changes here. So this is positive, it stays positive, then it turns negative. And so that's the only sign change we have, and now we can see that there's one negative real zero. Now using the fundamental theorem of algebra, we know there has to be a total of 4 zeros. If one of the zeros is a positive real and another zero is a negative real and there's a total of 4, then the last 2 zeros are non-real. And that's the only possibility for the zeros for this particular polynomial.